All right. Now let's look at what is lasso. Um, mhm. Okay, so you might wonder what does this lasso means? So it is short for list absolute, shrinkage, and selection operator. So it's a pretty long name, right? So people just use lasso for short. It's a fairly new method, and it's an alternative to ridge regression. Um, well, we talked about that ridge regression. It has the problem that it will never set the coefficients exactly to zero, even though it shrink towards zero. It never set exactly zero. But with lasso, we overcome that this disadvantage of ridge regression. So similarly as ridge regression, the lasso coefficients are estimated by minimizing this thing. So the first part is still the residual sum square. So RSS plus a penalty term. If you didn't pay attention, you might not notice the difference. Here, in this penalty term, we use the L1 norm instead of L2 norm. See here, it's absolute value instead of square, as in ridge regression. So this L1 norm in this penalty term is defined as the summation of the absolute value of all these elements in this vector beta. So again, this we only penalize on the coefficients for the covariates, not on the intercept. Okay, so lasso is similar, but we are minimizing, similar to ridge regression, but we are minimizing for this target, for this objective, instead of the penalty term with L2 norm. Okay, so there are many similarities between ridge regression and lasso. So similarly, the lasso will shrink the coefficients estimates to zero. And also the variates, the coefficients from lasso, it also varies from the non-model at lambda being infinity to the least square fit when lambda being zero. Okay, so in terms of lambda, they behave similarly, but the unlike the ridge regression, the lasso will shrink them all the way to zero. Exactly zero when lambda is sufficiently large. Remember in ridge regression, only when lambda goes to infinity, like theoretically infinity, it will be zero. But in lasso, it will goes to zero, shrink those coefficients to zero when lambda is relatively large. So basically, lasso is doing the real variable selection for us, and it will give us a sparse model. That means some of the predictors, their coefficients are set to zero, so they just go out of the model. So it will give us a simpler model with fewer predictors. So it gave us a sparse model, and you can actually see that when we do this coefficient plot versus this lambda value. So again, these coefficients are on the y-axis and the lambda values on x-axis. And we're still focusing on the example from the book, which is doing the regression on credit data. We have income, limit, rating, and student as the predictors. And we're showing here, you can actually well, let's follow this note here, moving from, focus on this plot first. And if we move from right to left, you can see that for the largest lambda in Lasso, it will give a model with only rating, right? Because this blue dotted line is the rating variable. So at a fairly big lambda, over 5,000, we start to have a non-zero coefficients for the rating variable. And if the lambda decrease a bit, and we find the student and limit predictors enter the model, they enter at about the same time, and then slowly becomes non-zero coefficients. That means they get into the model. And eventually the income is also selected as lambda gets smaller. Okay. And when we go the far left, we have the full least square model when lambda equal to 0. So for this bullet, it's behaved the same as in ridge regression. So this is showing you how the variables are selected into your model when you change the value of lambda. Okay, and similarly, this plot is plotting the coefficients versus the ratio of the L1 norm of Lasso regression and this least square estimate. And it's giving you the same information like when this ratio is small, that is when lambda is big. Okay, so when lambda is big, those betas are shrinked to 0. So lambda small, we have this rating in the model, and as this ratio goes up, that means lambda goes down. Later we have student and limit get into the model with non-zero coefficients, and later we got this income enter the model as well. Okay, so comparing the coefficients plot for Lasso and for ridge regression, you can easily tell how the Lasso just snaps those coefficients to exactly 0, where the ridge regression just slowly move those coefficients to 0, but only get to 0 at the theoretical infinity. Lambda goes when lambda is at infinity. Okay, so this is the difference between the Lasso and the ridge regression. And yeah, well, actually, yeah, we have mentioned this. Oops, we have mentioned this Lasso just directly get the coefficients to 0 when lambda goes when lambda increases. This is how Lasso just overcome the disadvantage from ridge regression. So in terms of, from this slides and going forward, we will kind of comparing these two methods, the Lasso and ridge regression, and trying to figure out how it comes, these differences between these two methods. So in terms of optimization, we know they're both minimizing a target function with different penalty term. Actually, we can rewrite their objective function as being this residual sum of square. We are minimizing the residual sum of square, but subject to different restrictions. So on the top, on this one, is for the Lasso. We are restricting the sample space for the beta the space for the beta being in this region, satisfying this condition. And for ridge regression, we are minimizing the residual sum of square, but subject to the limit, subject to the constraint, I should say, the constraint on here. Okay, so this is equivalent to say we are minimizing the RSS plus their penalty term. Okay, so let's take a look at of the lasso in terms of the constraint space for the beta. So if we think it's easier to plot it in 2D, so let's take the 2D, take a 2D example. So that means we have only beta 1 and beta 2. So this summation of the absolute value of those beta j's, remember here, the summation of the absolute value of beta j will be like this: beta 1, absolute value of beta 1 plus absolute value of beta 2 less or equal to s. So say this is the value of s. So s, negative s here. So we have this plot, this diamond area is the constraint area where the residual sum square will be minimized. So we have to find the value of beta 1 and beta 2 inside this area and to minimize the residual sum square. So this is intuitively showing you what the lasso is doing. So yeah, I said here, we essentially have a budget of coefficient values, and we find the best residual sum square within this constraint. So this is what this constraint is telling us. But for ridge regression, we are minimizing residual sum square subject to this constraint. So what is this constraint telling us is that we are choosing the beta 1 and beta 2, like beta 1 and beta 2 in this circle, in this circle area, this shaded area. This is our budget area for beta 1 and beta 2 and minimizing the RSS. Okay, so you can easily tell what are the exact difference between lasso and ridge. So in terms of the variable selection, what the impact of this constraint area for the variable selection process? Well, why that is essentially asking, why does lasso would shrink coefficients to 0 while the ridge does not? Okay, the short answer here is because for lasso, we have those sharp corners of the square, like here, those corners, where the corners, you know, that means when we selected beta 2, beta 1 is actually 0, right? At this point, beta 2 is at this value, but beta 1 is exactly 0, right? And also here, so this corners is indicating we are setting some of the coefficients being exactly 0. So this is why lasso can get to 0 for some of the coefficients. Or comparing to the rounded edge of the circle, this diamond shape, they will encounter these contours easily at the corners. Okay, comparing to this circle, the diamond is much easier to encounter this contour at these corners. Okay, so let's talk about the contour a little bit. So this red ellipses, they are the contours of different value of the residual sum square. That is saying all points on this one circle, on one ellipse, it share a common value for residual sum square. Okay, we are actually minimizing, finding the circle that will give us the smallest residual sum square. So that's why we're trying to get those like red ellipses and have it encounter or intercept with this constraint area. Okay, so this is if this is interesting to you, I'm just showing you like the very basic intuitive reason why this lasso will behave different from ridge regression. But if this is interesting to you, I would highly recommend you read the section of the book, the ISLR book. It's quite interesting, but there are like definitely some mathematics behind it. Okay, and if we compare this to lasso versus ridge regression, it's clear that the selection of variables to get us a smaller, a more interpreted model would be a big advantage of the lasso. But prediction accuracy also matters beside the interpretability. So we also care about prediction accuracy. Or in terms of the prediction, neither ridge regression or lasso will universally be better than the other. So basically, we can conclude that the lasso would do better when we have a relatively small number of predictors. Like we have a sense that only a few predictors would have substantial, like relatively large coefficients. So in that case, we would recommend to use lasso. But ridge regression will do better when the response is a function of many predictors, and all of them have roughly of equal coefficients, equal size coefficients. Okay, so this two would have their own like advantage, but the problem is that you never know which predictors would be the truth ahead of time. So it would be just depending on your prior experience with your data. So you might have a feeling which one would be a better choice for you. And we still use cross-validation to determine which is better for a particular data set. Okay, so cross-validation would be a good friend in terms of like doing data analysis. Okay, so yeah, so in terms of tuning parameter lambda, so excuse me, so typically the tuning parameter would be found by a grid search. So that means you choose a grid of values of lambda. Say we're tuning lambda. We get a grid of values for lambda and compute their cross-validation errors for each value in the grid. Okay, and you choose the one where the cross-validation error is the smallest. So this is a general way of saying, like we say, a grid of values for lambda. Well, for now, because we only have like one dimensional, or we have just one scalar, this lambda to tune. So we just have a sequence of lambda values. But when you have like more than one tuning parameters, it's more generally we'll call it a grade. Okay. Yeah, this is about the tuning parameter selection. And oh yeah, I forgot to say here. So normally we just choose the tuning parameter that gave you the lowest cross-validation error. But you can also use something called one standard error rule. So I have the next slide. This slide is showing you what is this one standard error rule. So in general, we will prefer a simpler model. You know, if those models, they are basically equally good, you would want to get the smallest or the simplest model. So this one standard error is helping us to achieve that. So if you do a k-fold cross-validation, so you know, when we do this k-fold cross-validation, when you randomize the data into training and testing, a different split of the data would give us like different prediction errors or any other criteria we use for, let's say, cross-validation errors. It will change. And we select the model, use this one standard error rule. That means we will get the mean square error for each model and then choose the model that is the smallest model with test error within one standard error of the lowest point on the curve. So let's, so this sentence is a bit long, but if let's say, if we look at this plot, say here, maybe like, somewhere here, it will be the lowest point for this cross-validation error. But we will not take this lambda, but we will like go, lambda is, oh, sorry. Yeah, we want to take a simpler model. Simpler model means we'll take a bigger value of lambda. Yeah, so let's see, this is the lowest point of the lambda. And we want to go one standard error further to select a smaller, a simpler model. You know, we're not necessarily selecting the one with the lowest cross-validation error because they performs like equally good, but we would prefer a simpler model. So we just move further a bit to choose a relatively small model. Okay, so this is just taking this plot as an example, but I'm just repeating what it's saying here. Normally, we just focus on the one will give us the lowest cross-validation error. But with this one standard error rule, you can move a bit because those models would be very similar. Like in terms of the cross-validation error, they are at the same level, but you want to choose the simplest model among those who give you similar cross-validation errors. Okay. So yeah, when they perform equally good, the smaller, the simpler, the better for your model. Yeah, I think this last slide is just showing you the cross-validation errors for different value of lambda and how you choose the one. Or you can choose the one give you the lowest value of cross-validation error, or you can move a bit to choose an even smaller model. And on the right-hand side, the coefficient estimates, it's also a function of the lambda. And if you choose this lambda being your, if this is your choice of lambda, this is the value correspondingly for the coefficients. Okay, so this is how you do cross-validation. You use different value of lambda and you compare their cross-validation errors. And then you pick the lambda. That way you use that for a ridge regression or like lasso regression. Okay, so this is just some side note about the tuning parameter selection. Okay, I think this would conclude the slides. we will have our lab as well for Ridge and Lasso.